Guys, let's see what the ninth question has for us. The ninth question says that in the Benson group method for evaluating standard enthalpies of formation of hydrocarbons, each group like CH3, CH2, etc. are assigned separate enthalpies of formation, and the heat of formation for hydrocarbon is additively calculated. On this basis, heat of formation, which is delta F for normal pentane, isopentane and normal butane, are respectively minus 147.3 kilojoules per mole, minus 156.6 kilojoules per mole and minus 126.6 kilojoules per mole. Now your job is to calculate delta F, which is the heat of formation of isobutane. Sandeep?
Yes, again this question looks something different, right? They
Right.
give us that it is Benson group method and they are using heat of formation for different things, right? Individual CH3, CH2 molecules, etc.
Yeah.
Right. So first understand the method what they gave.
Right.
See, in this method what they are doing is that for calculating heat of formation for any hydrocarbon, individually first they are calculating heat of formation for CH2 or CH or CH3, etc.
Right.
First they are calculating these things and they are calculating heat of formation for hydrocarbons.
Correct.
Right. See, in the question they gave delta F, that is heat of formation for normal pentane, right?
Yeah.
So what is normal pentane?
CH3, CH2, 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 CH3.
Yes,
Five
normal
carbons.
pentane means 5 carbon chain, right?
Right.
So it is CH3 and 3 times of CH2,
Correct.
right? And CH3. So, and they gave heat of formation for, let it name as delta F1 and delta F2
Yeah.
for isopentane, right?
Correct.
So similarly isopentane will be CH3, CH, CH2, CH3 and CH3.
Correct.
Yeah.
Yeah.
This one, right? And they gave for normal butane also delta F3, N-butane. N-butane again a 4 carbon chain molecule, right?
Right.
It will be CH3, CH2, CH2, CH3.
Correct. Yeah.
In the question they gave me delta F1 value, delta F2 value, delta F3 value.
Right.
And they asked me to find delta F formation for isobutane.
Okay.
Right.
Right.
So isobutane it will be CH3, CH, CH3, CH3. So for calculating delta F value of this one, I need to know individual heat of formation for CH3 and CH, right?
Okay.
And I can add them and I can get delta F value for isobutane.
Correct. Correct.
So my idea here is that I will form some algebraic equations for delta F1, delta F2, delta F3. Then I will find heat of formation for individual CH3, CH2 and CH.
Right.
Then I will use that values for calculating delta F formation for isobutane.
Correct.
Right. So let me consider CH3 heat of formation as X
Right.
and CH2 heat of formation as Y.
Okay.
Right.
Mm-hmm.
This as Y. So here I have 3 CH2.
Right.
So 3Y plus 2X.
Correct. So you're going to be using X for CH3 and Y for CH2 for the further equations also.
Exactly.
Okay.
And in my second equation I have here CH. Right. This is something different. I'll put it Z.
All right.
Right. So here my equation will be 1, 2, 3. 3 times of X plus Y for CH2 and Z
Right.
for CH. Right. And in my third one for N-butane it is 2 times of CH3 and 2 times of CH2.
Correct.
Right. So we have simple equations, just solve them. 3y plus 2x, we have one value.
So guys, as you can see, you have 3 variables and 3 different equations. It's easily solvable now.
Exactly.
Sandeep will show you how.
Solving these equations, we have 2x plus 3y, which is delta F1.
Right.
That one is minus 147.3 kilojoules per mole. Right. And we have 3x plus y plus z, it is equal to, that is for isopentane, right?
Right.
156.6 kilojoules. And for the third equation, 2x plus 2y, it is equal to minus 126.6 kilojoules per mole, right? By solving these equations, I can get values of x, y and z.
Right.
Right. So solving this, we get x as 42.6 kilojoules per mole and y as minus 20.7 kilojoules per mole.
Right.
And z, it is equal to minus 8.1 kilojoules per mole. I
Correct.
just solved these three equations. Right. So I need to find delta F formation for isobutane, right? So it is 3 into x plus z.
Right.
Right.
3 CH3s and 1 CH.
Yes, exactly. So delta F formation for isobutane will be 3 times CH3 plus CH.
Right.
So 3 into x plus z, which gives me minus 135.9 kilojoules per mole, which is the answer. So in this question, what they gave is that they gave us a new method, Benson group method.
Right.
And they are using this technique for calculating enthalpies of formation of hydrocarbon. So I just started with what we know, N-pentane, isopentane and N-butane.
Right.
And what we need to find out. So again, I used some, I did some algebraic calculations.
Yeah.
And we got the answer. Right.
Right. So can you tell our students once more, in what all cases can they use, can they have a variable for every such group?
Variable in the sense?
As in, you took CH3 to be X, CH2 to be Y, and then CH to be Z. Is it only in the Benson group method?
Exactly. See, just don't get confused by this method.
Okay.
This question they gave us for confusing us. See, till now we know only Hess law, right? In
Right.
thermochemistry for finding heat of formation. So they just want to confuse us by introducing new method.
Okay.
So here we are just using terms. Just don't generalize it. Either to use X or Y.
Okay. So guys, this was a really important question, and we got through the solution for it. Now we'll see what the next question is. Now in the 10th question you can see a set of statements. A. Sum of two part dependent thermodynamic properties is always part dependent. B. Work appears at the boundary of the system as well as inside the system. C. Work and heat are completely interconvertible in real life systems. And D. None of the above. You have to say which of the following statements are correct.
See, this is totally theoretical question, right?
Right.
So we'll verify each and every option.
Okay.
First, option A. Option A is sum of two part dependent thermodynamic properties is always path dependent.
Right.
Let us check. See, for suppose we have equation delta Q equal to delta U plus delta W. Right.
Right.
So, or else delta U equal to delta Q minus delta W.
Right.
Right. See, what is work? Is it a path function or state function?
It's a path function.
Path function.
Right.
And similarly, heat, it is also a path function.
Why is that?
Suppose T, if you have a system and I am supplying heat to the system,
Right.
I can maintain system at constant pressure and I can supply heat.
Yeah.
Or I can maintain constant volume and I can supply heat.
Right.
So, see, dq equal to du plus dw, right?
Hmm.
If I maintain constant volume, my entire heat, it will be converted into only internal energy since work done is zero.
Right.
But if I maintain constant pressure, it will be utilized to do work and to increase its internal energy.
Right.
So my heat supply, it depends upon the path, right? So in each path, whether I am doing it as in an isobaric process or isochoric process,
Basically,
right?
it depends on the type of process you are choosing.
Right.
Yeah.
So it is a path function,
Okay.
right?
Makes
Here,
sense.
so heat supplied, it is a path function,
Right.
and work done, it is a path function. And what do we know about internal energy, delta U? it is a state function, right?
It is a state variable, yeah.
Exactly. Since it doesn't depend upon how we reach that state.
Right.
It depends upon the only total energy in the system, right?
Yeah. So you're saying it's clear that...
Yeah. By adding two path functions, we are getting a state function, right?
Right.
So option A is wrong.
Okay, it's
Here they
clearly
gave that by adding two path dependent thermodynamic properties, we get a path dependent function,
which is not true as we saw.
which is wrong, right? So now let's look second option. Work appears at the boundary of the system as well as inside the system. So what is this? Boundary and inside the system. See, suppose that we covered in theory, right? See, if you have a system with some energy, how can this energy escape from the system?
Either in form of work or in the form of heat.
Exactly. So this energy, it can do some work,
Right.
or it can escape as heat, right? See, energy, it is property of the system, right? We can tell at any point that system is having this much energy,
Right.
but as far as heat is concerned, we can't tell system is having this much heat, right? Work, right?
Right.
We can mention only about energy. We can tell, suppose system is having E magnitude of energy,
Right.
but we can't tell that system is having W magnitude of work in it.
Yeah, it's either done by it or it's done on it. Yeah.
Exactly, right. So it always lies at the boundary.
Right.
This energy, it will try to escape from the system. So that will escape as work.
Right.
So work, it always lies at the boundary of the system. Right.
Right.
But not inside the system, right? Since it is not
Exactly.
property of the system.
Yeah.
So second statement, it is contradicting, right?
Right.
As well as inside the system. So option B is wrong.
Incorrect. Okay.
Yes.
So A
Now,
and B are wrong.
Wrong.
Let's move on to C.
See, option C tells us that work and heat are completely interconvertible in real life systems, right? See, we studied in second law of thermodynamics that, see, work cannot be completely converted into, heat cannot be completely converted into work, right?
Basically, yeah, no system is 100%
100%
efficient.
efficient.
Right.
So that is contradicting this one. So option C is wrong.
Right.
So we have only one thing, none of the options are right.
Okay.
So in this question, they are mainly concerned about three different theoretical concepts, right? About path function and state function, and about work. Is it system's property or not?
Right.
And third one, second law of thermodynamics. That's it.
All right. So we have an answer for you guys. We'll move on to the next question and see what happens there. So in question number 11, you have an engine that absorbs heat of 5000 kilocalories from a source at 127 degrees centigrade. Your job is to calculate three things. The first one, efficiency of the engine. The second one, useful work. And the third one, heat loss. Now, all of this, the heat's transferring to a sink placed at 27 degrees Celsius. So for the first part, the efficiency of engine, Sandeep will take us through.
So in this question, we are going to basically talk about Carnot cycle or the Carnot engine.
Right.
Right. So in the first part, we need to find efficiency of engine, right?
Right.
So what is efficiency of Carnot engine?
The temperature of source minus temperature of sink
Exactly.
divided by temperature of source.
T source minus T sink
Right.
by
T of source.
source.
Right.
Right. So in a Carnot engine, what actually happens is that, see, it will be absorbing some amount of heat
Right.
from a source placed at temperature T2, and the engine will do some work, W,
Right.
right? And remaining heat, that one, it will be sent into sink. This temperature is T1,
Correct.
right? So in the first part, we need to find efficiency, right? Here T2, it is 127 degrees centigrade, right?
Right.
In the sense 400 Kelvin, and sink temperature is 27 degrees centigrade, right? Implies 300 Kelvin. So efficiency will become 400 minus 300 by 400,
Right.
right? This is 1 by 4. Implies engine is 25% efficient, right?
Guys, there's one more thing you need to make a note of. whenever you're calculating efficiency, you have to convert the temperature into absolute temperature.
Exactly.
Right.
Convert into Kelvin.
Hmm.
Next, part B. They're asking about useful work. Right?
Hmm.
So, come to basic definition of efficiency. What is efficiency? It is that, see, how much work that we are extracting from the system
Right.
and how much we are giving to the system.
Exactly. So
Energy
you give
that we are-
energy to the system, then you take some amount out of it.
Exactly.
Right.
So, we are taking energy as work right here.
So what percentage of that energy are we putting to work, basically?
Exactly. So, that is work extracted or useful work
Right.
by how much that we are supplying, right?
Correct.
That is heat taken from the source,
Hmm.
right? In our case, efficiency is 25%, right?
Right.
We calculated in part A. So 0.25 equal to useful work by heat taken from the source. That is 5000 kilocalories.
Right.
So here it gives us that useful work equal to 0.25 into 5000. That
Correct.
is 1250 kilocalories. Right?
Right.
And coming to part C. Here they are asking us to find heat loss to the sink placed at 27 degrees centigrade, right? So heat loss to the sink. Come to alternate definition of efficiency.
Right.
Efficiency equal to Q2 minus Q1 by Q2,
Hmm.
or else T2 minus T1 by T2.
Right.
Right? So here it becomes 1 minus Q1 by Q2.
Hmm.
But our efficiency is 0.25, right?
Right.
25%. So Q1 by Q2 becomes 0.75.
Right.
1 minus 0.25, that is.
Exactly.
So Q1 equal to 0.75 into Q2, which is
Right.
5000 kilocalories.
Hmm.
Right? So Q2 becomes 3750 kilocalories. Right?
Right.
They asked us to find heat lost.
Hmm.
So this is heat going out of the system, right?
Right.
Here our system is this engine.
Huh.
So this one will be minus 3750 kilocalories.
Correct.
Right? This is heat lost to the sink. So in this question what we are doing is that we are using three different definitions for efficiency.
Right.
In the first case we use T2 minus T1 by T2.
Hmm.
That is temperature of source minus sink by temperature of source.
Hmm.
In the second part we use basic definition of efficiency. That
Right.
is energy that we are extracting and energy that we are supplying.
Correct.
And in part C we use one more definition, that is efficiency equal to Q2 minus Q1 by Q2.
Okay.
Heat absorbed.
Right. Now, can you tell me this? After I got the useful work done here, 1250 kilocalorie, could I have directly subtracted it from 5000 to find out how much of the heat was lost in part C?
You can do it. The reason why I explained this one is that to know about this basic form means we
Exactly.
can use efficiency, means we can calculate
Right.
efficiency from this formula also. See, here we have Q2 minus Q1, right?
Hmm.
Q2 minus Q1 means this is Q2 that we are supplying to engine, and Q1 that we are extracting from engine.
Right.
So where is Q2 minus Q1 going? That is work done.
Exactly.
So work done by this one, Q2.
Right.
So Q2 equal to multiplied by that one. We get it directly, right? So
Okay.
we can get it directly like that also.
So guys, another very important formula based question. We'll see what the next question has for us.